Hi, Chris DeLeon here. Another video practice programming for LMC 6310, Computers and Expressive Medium here at Georgia Tech in the Digital Media program, for which I'm a teaching assistant. Course website here, using processing as always for these demonstrations, which is free from processing.org, requires no setup or install. If you just want to follow along, if you're not a Georgia Tech student, hope you're welcome to. And this is the newest in a whole series of videos I made for this course. I encourage you, if you haven't, to go back and review some of those other ones to help set you up for what we're going to be doing here. As with my previous AI exercise, I'm going to be first outlining some steps that I hope you'll try to do on your own before we then look at how to make it work in terms of how I would do it. And this is a little bit simpler than the AI one. We want to focus on just an interesting problem about movement. The goal here is just to get like a mini golf kind of game where you can click to move the ball and get it into a goal pocket. We're going to start by setting the screen size to 640 by, let's say, 440. That's the size that's going to work better for me. Or, well, let's say 480. Whatever size you want, doesn't really matter too terribly. Let's just set the screen size bigger than the default at 50/50. Get a white ball of 30 by 30 pixels on a black background, starting at 100 pixels from the top and the left, centered, of course, on a coordinate. When you click, get the ball to shoot or roll towards the mouse and gradually come towards a stop. This is really the heart of this challenge, is to figure out, okay, how do you get a ball to move straight at the mouse? Because in the AI example, we had them moving at diagonals, we had them moving straight left and straight up and down. This is going to look at how to use trig or how to use vector geometry to get a ball to move straight at the mouse, even if it's not 45-degree increments of its current position. So when you click, you want to get the ball to shoot or roll towards the mouse and then gradually come to a stop. There's kind of two steps hidden in that one. Upon subsequent clicks, shoot the ball from its last position towards the new click. So this isn't just like projecting from a cannon where it started. You should just be able to keep moving around in relation to the ball's current position. Wherever you click, it should move from the ball where the ball was to where you clicked. 5, have a golf hole type circle on the bottom right. When your ball overlaps it, reset the game. Pretty straightforward there. And 6, only let the ball get hit by the mouse when it's stopped or moving slow enough. Show text on the screen someplace to indicate that the ball can be hit and is moving slow enough. So basically, you shouldn't be able to hit the moving ball if it was kind of like, say, a putt-putt metaphor. 7, count the clicks or strokes and display that number on the screen someplace. Reset it when the goal is hit. So each time you hit the ball, we're going to count up a number and show it on the screen. Like, first hit will go from 0 to 1, then to 2, then to 3. And when you've made it into the end goal, it's going to reset that back to 0 and reset the ball. And the counter. Those simple 7 steps, if you are warmed up with processing, especially if you've been following the previous videos, I encourage you to try this out on your own. Follow these steps. If you need to hear them again, I don't want to take up people's time who are following along. Go back, listen to them, pause, try to do each one on your own. It's really going to, I think, help you out to follow this exercise first, just from a verbal description level of the spec. But, assuming you've already paused the video, or you don't care to, either way, let's now walk through how I would do this, just for comparison to maybe how you might have solved it. Let me figure out a good space for this on the screen. Okay. Now, as always, we start with void setup and void draw. Setup will be called once the program starts. Draw will be called every frame. And these are in Unity, of course, the idea of start and update or whatever. So set the screen size to, I like to use 640, 480. It's an old DOS, an old Windows sort of resolution. When I press play, let me just double check that it's doing what I expect. There's a 640, 480 window. Good deal. Get a white ball of 30 by 30 pixels on a black background. Okay, background 0 is going to update my background to black. Every single frame is going to paint over where things used to be. Set the fill color to 255. And all red, green, and blue is going to be white for the ball color. I'm going to use ellipse to draw a circle. Remember, if an ellipse, the arguments are width, height, X position, Y position. We want 100 from the top and the left. And we want 30 by 30 for its width and its height. And just by setting the width and height to the same, we're going to get a circle. And the ellipse, unlike the rectangle, centers on the coordinate that is specified at, the X and the Y. Remember, the rectangle gives us the top left coordinate, whereas the ellipse by default gives us the center point. Let's press play, make sure we have a white 30 by 30 ball. There's 30 by 30, 100 pixels in the left, 100 pixels in the top. Steps 1 and 2 knocked out. Now we want to click to get the ball to shoot or roll towards the mouse. Again, this is the heart of the program. Step 1 is we've got to give that ball variables for its position, because as long as they're constants, that ball is not moving. So let's default the ball's X and Y to 100. we could have done this up here where we declared the variable. I'm just going to stick it here for now. And the ellipse, instead of drawing it at 100, 100, I'm going to draw it at ball x, ball y. Of course, you have to make sure that these variables are separated, or separate, different. You don't want ball x and ball x. And that's going to be our horizontal movement, our vertical movement. Press play. No motion yet, of course. But now that these variables are changed, we can move it. So if, for example, we had void mouse pressed. Now there's two ways we can use mouse pressed in processing. We can say if mouse pressed, and here we can say print line to debug to our console, mouse held. So check this out. Okay, sorry, saved it, just sort of compulsive habit this way by putting a file on it. We'll be able to get back to it. So now, whenever I hold down the mouse button, you can see down in the console, down below, it's in this area, constantly updating mouse held. Because mouse pressed is just checking a Boolean of is the mouse held down this frame. Draw is called every single frame, and if it's true that frame, it's going to do what's inside the if. Compare that, and comment that out, so it would be ignored by the computer, with void mouse pressed, print line, mouse clicked. Now see, when I hold down the mouse, it only shows up once down in the console when the mouse goes down, which is really what we want, because like I say, we want more of a putt-putt interaction. So we're just going to use mouse pressed. We don't have to do anything special to hook up mouse pressed, just like void draw and void setup, it's hooked into processing automatically. If we were in ActionScript 3 or something, we'd have to set up a separate event hook, but the kind of code we write would be the same once you set up a function to be called when the mouse is pressed. So we've got this. Now we want to shoot or roll the ball towards the mouse. First, let's just do a little sanity check, a little straightforward. Let's move the ball straight to where the mouse is when we click. This will confirm that we can update the ball's position. So when we click the mouse, we're going to take the coordinate of the mouse and feed it onto the position of the ball. Remember, equal sign in programming, single equal sign assigns left. So we'll take the value of the x for the mouse, put it on the x value for the ball, and when I press play, I can now click to reposition the ball. And again, because it's void mouse pressed instead of if mouse pressed, it only happens, even though I'm clicking and dragging, it only shows up where I first put the mouse down. Now to make it shoot or roll towards the mouse, we're going to need to have separate values for the velocity on each axis. Let's use a v for velocity component. So it's horizontal velocity and vertical velocity. I'm going to default those both to 0, taking this value, assigning it to both x and y. And now in draw, let's update the ball's position. Make an update. Do it before the. Let's make some functions already. Let's make a function called draw ball real quick, where I'm going to put the white in the ellipse. It's going to help me separate out my draw code. I'm going to make one called move ball, void move ball. And now in move ball, what I'm going to do is I'm going to add the x velocity and the y velocity, the current x and y velocity, to the ball's position, so that by setting these numbers, we can make the ball move. Because, you know, if they're not 0, it's going to constantly increase or whatnot from these values. So let's start off at 0. And now when I press the mouse, instead of updating the mouse position directly, let's just say, like, set these to, I don't know, let's say 5. Let's say 3 for now. Let's set these both, let's say 1 to 3, 1 to 2. Okay? When I click, I'm going to set the x velocity and y velocity to 3 and 2. Move ball, which is called every single frame, is going to take whatever I last set the x velocity and y velocity to, update the ball's position incrementally. So every single frame is going to move by 3 over, 2 down, 3 over, 2 down, 3 over, 2 down. As the directions are probably reversed for the camera. But when I press play, here we have a ball, and when I click, it just takes off moving in a constant line. We're partway there. We want the ball to gradually come to a stop. Okay, well, let's do that before we're getting it to go towards the mouse. Right now I'm just assigning just any old speed just to make sure that indeed when I click, the ball moves and keeps moving. As part of moving our ball, after we add the current x velocity and y velocity to the ball's position, let's decay the value. Let's say times, I don't know, 0.95. And if you think about what this is doing, is every single frame is taking, okay, times equals is the same as saying ball x equals ball x times 0.95. So these two lines are the exact same code, remember, which says takes the value that it was, multiply times 95%. So take off 5% and then save it back into the same spot we got the number from. So this is going to shave off 5% of the ball speed every single frame. So now if we play it, I click, the ball will burst and then slow down to a stop. This kind of use of decay value is extremely common in simple game programming. It's been rapid prototyping or whatever. And if we make this number closer to 1, like 9.7, then it'll take it longer to slow down because now it's only shaving off 3%. If I made this 9.9, it'll only lose 1% per frame. It'll roll much longer on one click. It's kind of like a friction value. And if I made it 0.9, even though it seems like 90% is a pretty high number, if you shave off 10% of its speed every single frame, it's going to really rapidly come to a stop. It's almost more like I'm kicking a cardboard box along the ground than rolling a ball. So let's go with a high number. Let's say 0.96. This must be like a reasonable value. It's got kind of a little burst to it. And of course, we could change how much speed we're giving it, which is what we're going to do next. Now we want to make it go towards the mouse. And here's the heart of what we're doing. Now there's two different ways we can handle updating the position of the ball. We can use scalar math by using a normalized vector, or we can use trig. I'm going to show you both of those, and they work for the exact same mathematical reasons. Float ang2. Let's see here for a sec. Okay, oops. So ang2 will be the angle from the ball to the mouse equals a tan 2. A tan 2 is for arc or inverse tangent. 2 means it's a 2-argument version. And this works for reasons that if you know trig, you're going to get why. If you don't know trig, you're going to be a little confused by this. But it's basically going to give us the angle from our ball to the mouse. It's taking the left argument over the right argument, doing the arctan on it. Now let's have a separate value for like ball speed. Let's say 5 is a good speed value. And I'm going to set ball x to cosine of the ang to the mouse times ball speed, ball y times the sine of it. And what is this crazy business? First, let me show you that it works, just to demonstrate that. When I click here, it shoots straight at the mouse. See how it goes directly at it no matter what angle it's in? It could be to the right of it, could be below it. Now, one thing people will often do when they're first trying to do this kind of thing, if they're following just the steps, is they'll use a lot of less than, greater than comparisons. The problem with that is you don't get this granular, nice angles straight at it, even if it's just a few degrees off. You only get 45-degree increments if you're comparing against, is it above or below on the screen, left or right of it. By finding the angle and then using sine and cosine, we can get direct translations of the speed. Now, to reverse engineer what the trig here is doing, so tangent, remember, is rise over run. That's the y over the x. And so it's our y is the mouse y minus the ball y. Our x is the difference in their horizontal positions. Again, so the a tan 2 function for trig built into processing, a lot of for the math programming languages, with a comma between the two is just taking the top over the bottom. So this is the tangents. Arctangent's reversing that to give us the angle. So we're getting the angle between the point we're starting at, ball x, ball y, and the mouse, mouse x, mouse y. Ball speed now is just being used as a scalar for how fast we want to push the ball, because cosine and sine give us the lengths in a unit circle for an angle of the legs of that triangle. And so we can use this as a percentage on that 5 as an operator. So if it's horizontal, straight side to side, then this will give us 1.0. If the line's going horizontal on a triangle, we're going to get 1.0, or 100% of the ball speed should be horizontal. And the other axis is going to give us 0.0, so we'll get 0 vertical speed. And the opposite's true at 90 degrees, where it's going to give us 1.0 for solid up and down speed, and 0.0 for no horizontal speed. And if it's at 45 degrees, we're going to get 0.707, the sine or cosine of 45 degrees, to give us the same speed of both. And the important bit of that is that 0.707 is accounting for the fact that if you just added the vectors together, 5 over 5 up, we would have actually longer vector. We'd be moving faster than 5 in total. If we're moving 5 by 5 independent, that 0.707 is keeping it within a unit circle, which allows us to jump around directly at the mouse. Now the other way we can do it, let's say you don't like trig, you're a little confused by this. Hopefully you're less confused by vector geometry, because that's the other way we can solve this, is we can say, let's see here, how do we want to start writing this? Dist to mouse instead. And as I showed in the previous example, we could write our own distance function. We're just going to use one here that's built into processing, dist. Takes an x and a y for one position, x and y for another. So we're going to find the distance from our mouse to the ball. We're then going to normalize the x value and the y value. What that means is we're going to put it on a unit scale. Okay, so here's mouse x minus ball x. So that's the total length we are along the x-axis. And by dividing by the distance to the mouse, it's going to put it on a 0 to 1 scale. Then we're going to do the same thing for y. That's going to tell us what percentage of its horizontal offset is the total distance to the mouse for x and y, horizontal and vertical respectively. Float ball speed equals 5. And what I'm showing here is completely equivalent. And in fact, if you look at the numbers, it's going to make sense to you as to y. But depending on what environment you're in, sometimes it makes sense to use scaled values, or depending on what you're trying to accomplish. Sometimes one or the other has slightly different ways you can tweak it. Same trick. By normalizing the vector, we're getting a value from 0 to 1 for each axis, which the hypotenuse for between the two will give us 1, or a unit vector. Speed we can multiply both times by. That's just going to make it get a bigger force. If we took it at 1, then we're just going to get a unit vector for ball speed, which is going to be probably too slow. 5 gives a little more kick. So either one of these is really doing the same thing. One just has an ATM2 operation, which is going to be a little more expensive if you're doing hundreds of thousands of calculations of these kind of things per frame. And the other is using a scalar vector. We could, of course, spare the distance call. This difference is already calculated as part of the delta. There's other ways we can normalize vectors and use a built-in p-vector or whatever. But the gist is that either one of these is equivalent of how to take an object that's somewhere on the screen and shoot it towards the mouse, or move it towards the mouse. So now we're done with step 3. Either one of these works. I'm partial to the angles. I find it's kind of nice to be able to use this method, because then if I'm going to have a random variation on it, I could say like plus equals random. I'm going to use the other notation I tend to not maybe encourage as much. This would be like between -4 and 4 degrees. So let's just see what happens when I do that. All right, I forgot. So this is on radians. So this is quite a bit. Let's say like 0.1, 0.1. So a random value between -0.1 and 1, and it'll randomize it a bit so it doesn't go straight at it, but has a little variation. And that's the kind of thing we do when we're operating at an angle level, as opposed to using the normalized vector in the same way. Okay, so that's the end of step 3. And again, I got rid of that randomization. That was just the demonstration. So on subsequent calls, shoot the ball from its last position towards a new click. We've actually completed 4 by default. 5, have a golf hole type circle on the bottom right that when ball overlaps causes the game to reset. Okay, well let's define that separately. Float goal x, goal y. Bottom right. So here, after I've set the size so that width and height are set, then I can set these to width minus 100, height to minus 100. So it'll be 100 pixels in from the bottom right. And notice I've set a variable on it, not because we're going to move the goal, but because this is going to help me keep track of, in code, its position. We'll let him have to think about what its position is. That's 100 from the corner. And it's also going to allow me to simplify the math for finding the distance between the two without hard coding the same number in different places. So let's draw the golf hole. I'm going to put it here so that it is between the background call. If we did above the background call, background would erase over it. And below, or before we draw the ball, so that the goal will be drawn under the ball when they get close to each other. Goal X, goal Y. Let's also come up with one called like goal width. Let's make it like, I don't know, 50. Okay, declared it here as 50. Okay, the same value for width and height. Now we should see a hole there in the corner. There's our hole. When the ball overlaps it, cause the game to reset. Remember how we did this dist function earlier? Dist between, actually let's put this in move ball. So I left that code the same. move ball, and so on. But here in move ball, I'm going to check after I've moved it if distance between ball x, ball y, comma, goal x, goal y is less than, let's actually create a new value here for float ball width. Okay, this is going to help us make math that makes more sense in this comparison. I'm going to declare that 30 here. And now down in the draw code, I'm going to replace the 30 here that was hard coded with ball width value is less than ball width plus goal width times 0.5. So that's going to take half the width plus half the goal, basically the radius of both circles combined. Because if the two radiuses are together less than the distance between the center points, then we know that the circles have overlapped. Then we're going to reset the ball, which let's make a function called reset ball. There's our reset ball function. I'm going to define it up top. Void reset ball. I'm going to put this code in there. Basically, this is going to reuse the same code I had in setup. I'm going to move it to its own function that sets its initial position, zeroes out its velocity, sets its width, which we don't need to redo, but no harm in it. And I'm going to also call that when we are within a certain distance of the goal. Check and make sure that that works. Bump, and you'll see right there when we bump into the goal from any direction. Like I say, if we're less than the sum of the radiuses, then we are overlapping and it's going to reset the ball, which is step 5. Step 6, only let the ball get hit when it stopped moving. Well, okay, well, how would we do that? So let's come up with a metric for what that means. So if we click, then we want to move the ball. I'm going to get rid of this vector solution. Okay. How do we find the speed of the ball? Let's say current ball speed equals dist 0, 0, ball xv, ball yv. And remember this, so this is just a simple way to find the length of that vector, the magnitude of it. And there's a p vector built in, but I find this is handy to think more about the math at this level. So there's our current ball speed, because it's from the origin to the vector x velocity to y velocity. So combination of the axes, but not just adding them together. And if we are going over a certain speed, over too fast to hit, then we're going to bail out of this function. And then we need to define that constant, let's say 0.3, for example. And I do this thing where it's an old C habit, all capitals, underscores if it's constant, final to let me know that I can't reset this value elsewhere in the code or it'll throw an error. And so if it's going too fast to hit, see, I can keep clicking and it won't actually let me hit it until it comes to a stop. If I build this into its own function, Boolean is ready to hit. Let's kind of do the opposite. Okay. Gonna have a return value. I'm going to find the distance. I'm going to find the speed of the ball currently. And if it's less than the value of too fast to hit, then we're ready to hit it. So if that equals false, return. It's just going to externalize it, Boolean, so it's expecting a return of a Boolean. This is a true-false comparison. And I can use this same if statement down here in the draw code. Let's put it near the end because it's like UI stuff. Going to get rid of the false, which is by default checking to see if it's true. And if so, I'll put a text up on the screen that will say ready to hit. 1515 should be a good coordinate for it. And now when it's ready to hit, it'll say ready to hit. Until it is, it won't reflect that. But by tying it to that same shared function, this will only show up when a click will actually let me hit it. I think we got one more step. I got a URL down below, sort of the sample answer. Count clicks and strokes and display it on top of the screen. Should actually be pretty straightforward. Int stroke count. When we reset the ball, let's reset the stroke count to 0. Just an integer, which means this is already going to be zeroed out when the program starts. because we're calling reset ball and setup. And now when we move the ball, so only if we've gotten past the ready to hit, because we don't want to count strokes if you click while the ball's in motion. Stroke count plus plus is going to add to that number. See that right there? Again, we could say plus equals 1, could say equal, we could say stroke count equals stroke count plus 1 or whatnot. All the same, plus plus is shorthand for just add 1 to this number and update it to that new value. And so then we need to display that number on the screen. We always want this one to show up, even if the ball is rolling, so we're going to put it outside the isReadyToHit function. Check. Strokes plus ball strokes. Let's put the left side 85 pixels in, also 15 pixels from the top. And when I press play, see here it says strokes 0, strokes 1, strokes 2. It ignores my clicks between strokes. 5 strokes, 6 strokes, and it resets when it hits the goal, back to 0. So that's all there is to it. Relatively straightforward example, but this notion of being able to use vectors, separating the x and y velocity, being able to decay the speed by removing a percentage every frame, that's step 4. That step 3 is a really critical thing to wrap your mind around, to practice doing, to find a different context. It's how we aim projectiles like cannon shots or bullets in different directions unless we're doing a ray cast. Rockets and projectiles of all sorts. Throwing a ball can be handled in this way. Oh, and a little trick, by the way, if we wanted to see a side view, is of course we could add to the ball's y velocity. I'm going to do this kind of a lazy way because I'm running out of time for now. But if I added a simple constant to y velocity every time, say 0.2 to y velocity, now it's got gravity to it. Oops. But we're not actually handling bounce. If I wanted to make it bounce, if the ball's y is greater than height, so we've fallen below the edge, and we're currently going downward, then ball x will equal negative ball y velocity will equal negative ball velocity, so it should now bounce off the bottom. Bounce. If I gave it some more hit force, there's all kinds of things we could do to make this into like a side view thing. Bump, 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 bump. Oh, ready to hit is now not detecting. I think this is a slower value. All right, but see now I have kind of this side view golf game instead by giving it some gravity and a bounce ability where I can still hit it into the goal and reset. There's lots of things you can do to play with these values. They're super handy to know about sine and cosine and a tan too to find the angle. Or, like I said, use the normalized scaled vector instead. I'm having too much fun. I'm going to turn that off. Just to find how to take the speed that you want and then make it into separate component vector values to add on the x and y velocity. Or if you're in 3D, x, y, and z. Hopefully it's been handy to look at how to get this just ball motion going. I think at an 8th step, yeah, we're going to have the ball bounce off the edge of the screen, which I already showed you the basics of here. Of course, you'd extrapolate that to the other axes. Thanks for following along. Hopefully you'll stick to this. If you haven't subscribed, I encourage you to subscribe to his channel. There'll be more program videos coming up soon with other example tutorials of some basic processing programming for real-time interactive simulation stuff. This is Chris Deleon for LMC 6310, and hopefully I'll see more of you soon. Thanks.